participants joins later. So till now, 3 units we completed. In 3 units, we studied different reactions. The first unit we talked about single reaction and multiple reactions, how to write the rate and all. Then in second unit, we talked about the different types of reactors, flow reactor, batch reactor, what will be the performance equation for it, and which reactor is better for what particular conditions. In third thing, we discussed about multiple reactions and multiple reactors. So if there is a multiple reactions, either it is a parallel reaction or a series reaction, how you can treat that kind of reactions in the reactor, that we discussed both by qualitative and quantitative. Not only series parallel, even a series parallel combination also. Both qualitative and quantitative description will be there. Qualitative, generally it will be given in terms of diagrams and curves. Quantitative, it will be given in terms of the equations, right? So now we'll come to the fourth unit. This unit is quite interesting now, because till now we discussed that your temperature and the pressure is not going to affect the reaction. That is, the reaction is isothermal. But most of the cases, the reaction will not be isothermal. A lot of exothermic reactions will be there. A lot of endothermic reactions will be there, where you need to supply the heat or you need to remove the heat. If there is a temperature rise or temperature decrease, how the rate is going to change and how you will incorporate that change into your design expressions. That is what this unit is all about. So fourth unit is the temperature and pressure effects. That is, if there is a temperature and pressure which is going to change, then how you will incorporate that into your design expression. So in this equation, we will study about non-isothermal. Till now, we discussed about isothermal. Again, the reactions are homogeneous here also. So entire CRE1 is only about homogeneous. If there is a non-isothermal and non-homogeneous like heterogeneous, that it becomes still difficult, right? So adiabatic reactors, the reactors which are adiabatic, and the rates of heat exchange for different reactors, because heat is either liberated or you are increasing the temperature. So how, if it is going to be a exothermic process, then how you are going to remove the heat, right? So you need to remove the heat, because your K is a strong function of temperature. K is K naught into e power minus E by RT. Even a small change in temperature, the rate will shoot up. Then the design of a constant heat input and constant heat transfer coefficient. I think you know what is heat transfer coefficient, right? So heat what do you call heat transfer, you might have studied. Heat transfer coefficient, mass transfer coefficient, all that. Then the operation of batch and continuous reactors. Then optimum temperature progression. That's a very important topic. OTP. It's not the OTP what we get in cell or mobile messages. It is optimum temperature progression. That means for exothermic reactions, there will be an optimum temperature where you get the maximum rate. So how you can operate your reactor at that maximum rate, decreasing your, that is removing the heat. Right? That is called as OTP. It's all 2 marks questions also is very important. So before going to this unit, we need to study some of the thermodynamics, right? Because whenever there is a temperature which comes into picture, then the basic knowledge of thermodynamics is required. Can anyone tell what is the difference between thermodynamics and heat transfer? Both are same. Thermo means heat, dynamics means transfer or movement. So thermodynamics is nothing but heat movement or heat transfer. Whereas heat transfer subject is also heat transfer. Is it both same? You are studying both. Heat transfer you are studying, thermodynamics also you are studying. Yeah, what could be the reason why you are studying both? If both is going to be same, yeah. Yeah, anyone can answer that. Why you are studying thermodynamics and why you are studying heat transfer? Both are same, right? Thermodynamics is heat which is in motion. Heat transfer is also heat which is in moving. That is, heat is being transferred. Yeah. Any idea? Yeah, this is also an open-ended question. So, what is heat transfer and what is thermodynamics? Why you are studying both? Yeah, you might be. Some of you know the answer, but you don't want to talk here. Is that correct? Yeah. Anyone? Yeah.
So thermodynamics is a qualitative study, sir.
Mm, mm. Then heat transfer.
Whereas we are studying quantitatively, sir.
What do you mean by qualitative and quantitative there? Different meanings will come, qualitative, quantitative. What do you mean by qualitative and what is quantitative? Yeah. The answer is correct. Yeah, I just want some more information on it. Yeah. Yeah, what is qualitative and what is quantitative there?
Sir, in heat transfer, our area of interest is how much heat is transferred, sir.
Okay. In
We are
thermodynamics?
measuring in thermodynamics, we are just finding the feasibility, sir, whether it will happen or not.
Huh? Finding the? I didn't get it.
Feasibility, sir. Whether the
Feasibility.
process will. Yes, sir.
Feasibility. Good point you raised. Feasibility. Yeah. Any other people want to talk? It's a good question. Basic. Why you study heat transfer and why you study? There is something in heat transfer which you won't study. That is why you are studying in thermodynamics. Yeah. Both is same. Heat transfer only. But in heat transfer, there is one disadvantage, or in thermodynamics, there is one disadvantage. That is why you are studying the heat transfer. Remember, heat transfer is all about rate, rate at which the heat is being transferred. That is per unit time. How much will be the heat which is being transferred? So it gives you, as the boy told, quantitative. Yeah, that's the rate. How much heat is being transferred per unit time? That is the rate. Any rate is nothing but per unit time. It is second, minute, or hours. Whereas in thermodynamics, you'll study about the amount of the heat which is going to be transferred. But you never study how much time it requires for it to transfer. Whereas in heat transfer, we'll study how much time it is requiring for the heat to be transferred. And as you, one more boy told, you study about the feasibility of the reaction. That is whether the reaction is feasible or not. Right? So that's the basic thing. What the disadvantage or what you won't study from thermodynamics. Generally, you study from heat transfer. Heat transfer is all about a rate, as he rightly pointed out. It is quantitative. How much per unit time, or flux? How much is the mass flux? Heat flux. What is flux? What is rate and what is flux? Any idea? What is heat flux and heat rate of heat transfer? Both are same.
Heat flux is per unit area, sir.
Ah, unit flux is per unit area will come. That is why whenever you talk about heat flux, mass flux, in denominator you get meter square. That is the area. Whenever we talk about rate, we get per second, per unit time. Time will be in the denominator, right? So that's why your heat transfer coefficient, watt per meter square Kelvin. How much of the heat is being transferred per unit area per unit time. So that's the thing, right? That is. Go to the temperature and pressure effects. Why this temperature and pressure effects will be more important? Now let us consider a reversible reaction. A is giving you R. Again, we still talk about irreversible only here. If it is a reversible, then again back reactions also you have to put. Is carried out adiabatically in a PFR. So you take a PFR, adiabatic. So neither the heat is added or removed. So it's a liquid phase exothermic reaction. You are assuming that it is an exothermic reaction. The temperature of the reaction mixture will increase because it is exothermic. With the time, the temperature will increase, and a conversion also will increase along the length of the reactor because the reaction is happening in the length of the reactor. Therefore, your temperature and the conversion will increase along the length of the reactor. Right? So where it is going to affect? Now, you know that tau is the space time is V by V naught, that is volume by volumetric flow rate. That is equal to Ca naught into 0 to Xa dxa by minus Ra. This is nothing but the plug flow equation. Or tau by Ca naught is 0 to Xa dxa by minus Ra. Let us take it is first order reaction. Ra is K into Ca. But we know that Ca is Ca naught into 1 minus Xa. Then if you substitute the K minus Ra here, then tau is V by V naught is equal to integral 0 to Xa dxa by K into 1 minus Xa, because Ca naught get cancelled out. Therefore, K into Cxa. If you want to do this differential or integral, you take this K outside and then do this integration. Dxa by 1 minus Xa is minus ln Xa, and if you substitute the limits, you get the design expression for the first order reaction. This is what till now we did. This is for an isothermal reaction. But if the temperature is going to change, this fellow, the K fellow, which you are taking outside the integral, because this is a constant at a particular temperature, this fellow cannot be taken out just like this. You have to keep this fellow integral inside the integral. You can write K as K naught into e power 1 minus K is K naught into e power minus e by Ra. If you write it, then that fellow is a function of T is a function of this particular thing. Therefore, there will be two terms which you need to integrate. Then you have to do integration by parts. One by right. So that is what it will happen. For the isothermal operation, you are taking K outside and then doing this. But for a non-isothermal operation, you cannot take like this. That is what is. We know that the rate constant is a function of temperature T, and its variation with T is given by Arrhenius. K is K naught e power e minus e by RT minus E or EA is the activation energy, and K naught is the pre-exponential factor. For a particular reaction, this pre-exponential factor will not change with the temperature. So if you are writing at a particular temperature K1, K naught into e power minus e by RT1. This is at any temperature, and this is one temperature T1. So how you can write, I know the K at a particular temperature. I want to find out the K at another temperature. Then what you do? You divide one over the other. Then what you get? K naught by K naught cancel out. E power minus e by RT divided by e power minus e by RT1. Now K is a function of T. Therefore, K1, K you want to find out. You know the temperature at K1. You know the rate at the K1. We need to find out the K at any temperature. We can find that by using K is K1 exponential. This is nothing but e power minus A, e power minus B. You can write as e power minus A minus B. So exponential E by R is common. 1 by T minus 1 by T1. Correct? minus I took it common, I think. This is if it goes step positive, you can put this minus. I think there is one minus. Or if you take this, this is T1 minus T2. It depends on what temperature is higher and what temperature is. You can rechange that particular one. Now K is K1 into this particular thing. This K1 we already know at a particular temperature. You need to find out the K at any other temperature. Any other temperature. This is the expression for it, which we already got in the first unit. So now you need to substitute minus RA this particular thing, because here K you have to substitute this. Only K1 is removed outside. Now if you substitute that, tau is V by V naught integral 0 to XA dXA by, this is the K. K1 is K is K1 exponential E by RT minus 1 by T minus 1 by T1 into 1 minus XA, because this fellow is there now, 1 minus XA. So 1 minus XA. Now this K1 is constant because at a particular temperature, this is constant. I can take outside, but this fellow is going to change. So you need to find the integral for this entire one. This itself is difficult. If it is square, that is second order, third order, all that. But now you are having this fellow also into picture in the integral. So that is where the difficulty comes. Right? This is the difference of temperature. If there is a isothermal conditions, you are safely neglecting K outside and then doing the integration. Your life becomes very simple. But this is going to change. Then you need to integrate this entire one. This is only for a first order reaction. If there is a second order reaction, you get square, even cube, even 4 times. That itself is going to be a big task to calculate this fellow. So now you understood how difficult it will be. Again, you need to do some partial fractions and all, and then calculate that A, B, and then substitute the limits to calculate the final expression, right? So this is what we will be studying in this 4th unit, right? Yeah, any doubt here? Yeah, as usual, you don't want to talk anything here. Okay, then. Let us go to the next slide. Someone talk?
Yes, sir.
Okay, let us go to the next slide now. So now you understood what is going to be changed in the 4th unit. That K fellow will change. The K fellow you cannot take outside constant. The K fellow you have to keep inside the integral and do the integration together along with either CA or XA. Let us see some thermodynamics now, because we require some of the thermodynamics. We know this is all school stuff, which I just put. Heat of reaction from thermodynamics. So 3 types of reactions. The standard heat of formation one, standard heat of combustion, and standard heat of reaction. The standard heat of formation is given in terms of delta H, F. They put one subscript 0 like that. That tells it is standard. Standard heat of formation. F stands for formation. C stands for combustion. R stands for reaction. Right? So that's 0 at the superscript and F at the subscript. Right? So standard heat of formation. What does that mean? The name itself suggests it is formation. The name itself suggests it is combustion. The name itself is suggesting it is a reaction. So generally standard heats are all at standard temperatures and pressures. Generally it is 25 degrees centigrade and 1 atmosphere. And if you are using some Kelvin, then it will be around 298 Kelvin, right? 1 atmosphere solve. So standard heat of formation, what is the definition of it? The heat of a reaction is a heat of a reaction. These are all heat of a reactions, but different values will come. What is this for formation? It's a heat of a reaction when 1 mole of a compound is formed from its elements when all the reaction species of a reaction are at their standard states. So all the elements you take, if they are at a standard states, 25 degrees centigrade and 1 atmosphere, how much of the heat is being either it is coming out or even it is reacted. That is nothing but the heat of formation. So either 1 mole of a compound. So the product which is formed is 1 mole of a compound is formed from its elements, right? That is the heat of formation, standard heat. Standard heat of combustion, delta H superscript 0 and C. C is for combustion. Combustion, is a burning. The heat of reaction of 1 mole of substance. Again, this is one compound and 1 mole here. With the molecular oxygen to yield specified products with both the reactants and products are at the standard states. So one heat of 1 mole of a substance is there and it is reacting with oxygen to give you the products. Again, both the reactants and the products should be at the standard states. That particular thing is called as the heat of combustion. So it is nothing but with presence of the oxygen, it is being reacted. The third one is that standard heat of reaction. Standard heat of reaction. This is the heat of a reaction. Generally, it is an enthalpy change, which we talk about enthalpy change, resulting from the reaction when both the reactants and products are in their standard states. So the reactants are at 25 degrees centigrade and the product is also at 25 degrees centigrade. The difference between the products minus the reaction or the enthalpy of the products, the sum of the enthalpy of the products minus the sum of the enthalpy of the reactants will be equal to delta HR. That is nothing but the standard heat of reaction. Here, one important thing is both the products and the reactants should be at 25 degrees centigrade. So that is what this delta HR is sigma delta HF, that is for products. This is nothing but the sum of the sum of the standard heat of formation of the products. The products may be if there is only one, then you will put only one. If there is a giving you B plus C, then you have to put standard heat of formation for B and standard heat of formation for C. That is for the products minus standard heat of reaction formation for the reactants. If there is only one reactant, only one you will put. If there are two reactants, you will put the sum of the two. So delta HR is sigma. Sigma always talks about sum, whereas pi talks about multiples. That is multiplication, right? So that is the standard form which we use in engineering. Sigma is always sum. Pi is multiplication. That is the product. Sigma of delta HC, either you can write delta HR in terms of formation of the products minus the formation of the reactants, or we can write delta HR as the combustion of the reactants minus the combustion of the products. That's up to you how you write it, right? So we'll use this particular thing. We'll take one example. AA plus BB gives RR plus SS. So small a, b, r, and s are the stoichiometric coefficients, and capital A, B, R, and S are the reactants and products. A and B is the reactant, and R is the product. Now let us write delta HR for this reaction. Delta HR standard heat is, what is that? For the product first you have to write, and then the reactants. So we write in terms of formation first. So R is the stoichiometric coefficient R into delta H, delta heat of formation of R, the sum of the products. So there are two products now, R into formation of R plus S into formation of S. This is the entire thing for the product minus, again, reactants is A and B. So A is the stoichiometric coefficient of the reaction there. Delta H formation of A plus delta H formation of B. So this is the sum. This is the sum. Either you can write formation or the combustion C, right? So both you can write. There are two types of reactions, either heat is evolved or it is absorbed. One is exothermic and the other one is endothermic. Exothermic and endothermic. And depending on the following factors, the nature of the reacting system, the amount of the material reacting, temperature and pressure of the reacting systems, this particular delta HR will change. This delta HR will change if, depending on the types of the reaction. If it is an exothermic reaction, it gives negative. If it is an endothermic reaction, it gives positive. And if that depends on this nature of the reacting systems, amount of the material which is going to be taken, then the temperature and pressure of the reacting systems, right? So this is a very important thing, how you write the delta HRs. So we'll do some problems so that we get comfortable with these equations, right? So let us use one more thing in this. Now, this is the reaction. AA, BB gives RR and SS. Now, we are assuming that the reactants are at a 25 degrees centigrade. Even the products are at 25 degrees centigrade. The reactants are increased to a temperature, some other temperature, and even the products are also increased to some other temperature. So either the reactants can react at a because reactants can react at a standard temperature 25 degrees centigrade. The products are formed and the products is increased to a temperature T2, or the reactant can increase to a temperature of T2 and then the reaction will occur. Generally, this will be given. You need to find out this. That is, at a temperature, your delta HRs will be given. At a temperature which is higher than that, how to temperature you need to calculate. For that, there is an enthalpy change from this T1 to T2, and for the reactants, and for the products also there is an enthalpy change. Let that enthalpy is delta H3 and delta H4. Delta H4 is for the reactants going from T1 to T2, and delta H3 is the enthalpy change in the products which from T1 to T2. Whereas delta H R1 is the delta H of the reaction at 25 degrees centigrade, and delta H R2 is the delta H of the that is the reaction at another temperature, right? So we need to calculate this fellow. So that is what he just delta HR1 is the heat of formation or heat of reaction, is known for this reaction at a temperature and pressure. Pressure is 1 atmosphere, temperature is generally around 25 degrees centigrade. Delta HR2 is the heat of a reaction is desired at the same pressure but at a different temperature. So this is what you need to calculate generally. At high temperature, how much is the heat of reaction? The delta H3 is the enthalpy change involved in heating of all the products from T1 to T2. Whereas delta H4 is the enthalpy change involved in heating of all the reactants from T1 to T2. Now, there are two cases here. One is keeping the reactants at T1, then reacting the reactants to give you products at T1 and then increasing the temperature of the products to T2. That is one case. The other case is increasing the reactants to T2 and then reacting it to give you the products at T2. So either you can go like this or like this. In both the cases, there should be equal. Am I right? If I go like this or like this, it should be equal. That is what I try to equate now. Delta HR1 plus delta HR3. So delta HR1 plus delta H3. That is, the reactants are reacting at temperature T1 and products are being formed, and then the products are increasing to temperature T2. That should be equal to the reactants increasing to T2 and then the products are formed. So delta H R1 plus delta H3 should be equal to delta H4 plus delta HR2. That is what I put. Here, important thing is we don't know what is delta HR2. That is the heat of reaction at a higher temperature. We don't, right? So we need to calculate that. Yeah, just go through this. I'll just come to it. Yeah, we'll continue. Thank you for staying there. So enthalpy is a point function. So point function, this enthalpy should be equal to this. Therefore, the enthalpy of delta HR1 plus delta H3 should be equal to delta HR2 plus delta H4. What is enthalpy? This delta H is nothing but T1 to T2 Cp dash dt. Enthalpy is nothing but a constant pressure. How much is being changed delta T, that is T1 to T2. So Cp dash, yeah, I'm putting, whenever I put a dash, it is for a product. Whenever I am not putting a dash, it is for the reactant, right? So delta H3 is nothing but the product which is going from T1 to T2. Whereas delta H4 is the reactant which is going from T1 to T2. So that is why a dash I am putting T1 to T2 Cp dash dt, where Cp dash is the total heat capacity of the products, and delta H4 is C1 T1 to T2 Cp dt, where Cp is the total heat capacity of the reactants. So dash I'm putting just to differentiate between the products and the reactants. Now I substitute delta H3 and delta H4 in this fellow. Then I get delta HR1 plus T1 to T2 Cp dash dt is delta HR2 plus T1 to T2 Cp dt. We know this delta HR1, that is here, the standard heat of reaction at 25 degrees centigrade or at a 1 atmosphere and 25 degrees centigrade. We know that, but this we don't know. We need to calculate this. So knowing this, that is what delta HR2, that is what is unknown, is delta HR1 plus, so you're taking this fellow, keeping that fellow constant here, you're taking this side. So T1 to T2 Cp dash minus Cp into delta T. Correct. What is the Cp dash minus Cp? Is nothing but standard heat or total heat capacity of the product minus the standard heat total heat capacity of the reactants. That is nothing but delta Cp. So delta HR2 is delta HR1 plus T1 to T2 delta Cp dt. Now what is this delta Cp? Delta Cp is nothing but heat of total heat capacity of the product minus the total heat capacity of the reactant. What is the total heat capacity of the reactor products? Is nothing but R into CPR plus S into Cp. That is heat, what do you call it? Heat capacity of the reactant R product. Sorry, heat capacity of the product is into its stoichiometric coefficients minus, again, A is the stoichiometric coefficient, heat capacity of A is S into heat capacity. So it should be not a S, I think this should be around, what is the reaction? B, sorry. This is, sorry, there is a mistake here. It should be B, right? Stoichiometric coefficient into the heat capacity of the B. So if I substitute this fellow here, then I need to integrate. Then I need to integrate and substitute the limits. That is what I do. But we know that this Cp, what is Cp? Cp, I can write Cp is a strong function of temperature. Cp is the molar heat capacity. It is written as temperature. So Cp is alpha plus Bt plus gamma T square, where alpha, beta, gamma are the coefficients for a particular reactant. T is the temperature in Kelvin. Cp is the heat capacity at T, which is in joule per mole Kelvin. So Cp is this. Now you need to write the Cp's for the reactant, product, and then the reactants. What is for product R? Cp, alpha R. This alpha, beta, gamma are the coefficients of a particular reactants, right? For that particular reactant, you have to see from the tabular columns what is alpha, beta, and gamma. So alpha R, beta T, gamma R T square. This is for R, like that S, like that A, and B. Now, if I substitute these fellows here, CPR, CPS, CPA, CPB, then you land into big thing, because Substitute all the terms into delta PC. So where delta CP is delta alpha, delta beta T, delta gamma T square. What is this delta alpha, delta beta, delta gamma? Delta alpha is nothing but alpha of the sum of the products minus the sum of the reactants. That is what here. Delta alpha is R alpha R plus S alpha S minus A alpha A minus B alpha B, because I am substituting all this in the previous one. So sum of this minus sum of this. Again, it will have its stoichiometric coefficient. That is what. Like that, delta B, delta beta is R beta R, S beta S minus A beta A minus B beta B. Like that, gamma is again R gamma R plus S gamma S minus A gamma A minus B gamma B. Now, this is the final form of the equation. This delta P, you have to substitute here. Delta P, delta CP is nothing but delta alpha plus delta beta T plus delta gamma T square. Now, if you substitute in that, this fellow, and then integrate, because this we need to integrate. That is what we are doing. Substituting delta PC in the equation, delta HR2 is delta HR1 plus T1 to T2, delta alpha plus delta beta T plus delta gamma T square dt. So each term, if you do, there is no T here. Therefore, delta alpha is constant. Dt, the integration is T. So substitute the limits T2 minus T1. Then the next integration is delta B. Delta B beta is constant. T into dt is T square by 2. So T square by 2 is here. T square, if I substitute the limits, T2 square minus T1 square plus gamma T square dt is integral is T cube by 3. So 3 T cube, if I substitute the limits, T2 3 minus T1 3 or cube, right? So this is the equation. With the help of this equation, we can calculate the delta HR at any particular temperature, knowing a delta HR at a particular temperature. This T1 is known. T2, let it be 25 degrees centigrade T1. T2, we need to calculate at 65 degrees centigrade. So delta alpha, delta beta, delta gamma, they should give, or they have to give the deltas, gamma, delta, beta, and all that for the reactants and the products. Knowing this, this also will be known. Then we can calculate delta HR2. So this is with the help of this equation, we can calculate the heat of reaction at a temperature T2, knowing the heat of reaction at a temperature T1. So this is how it will be written. Delta HR2 is delta HR, that is the standard heat of reaction at standard, plus delta alpha into T2 minus T1 plus delta beta by 2, T2 square minus T1 gamma by 2. Now, what is this delta alpha? This particular thing. Either this equation or this equation you can use, right? This is at any temperature, right? So that any temperature, instead of T2, we put T. Any temperature you can take, right? So knowing what a particular temperature, you can calculate. So this formula is very important. This already you might have studied in your thermodynamics, or even I think school +1 or +2 also. I think you might have studied this. So based on this, you need to do some problem to calculate the heat of reaction, right? That we can do a bit later. We can either use mean, because these CPs are very difficult to do, because CPs you have to do like this, right? So we can take some mean. That is what is there. If the mean heat capacities are known for the reactants and products, we can put delta CP bar. That is nothing but a mean, right? So whenever I put at a bar, that is nothing but a mean. So that no need for you to write the different equations, right? So either of the equation you can use. Either if you know the heat capacities, all heat capacities of reactants, products and all, you can use this. Or if you know some of the heat capacities mean, heat capacities, then you can use this equation, right? Yeah, let us go to the chemical equilibrium now. What is chemical equilibrium? First, we need to know about the equilibrium state. What is equilibrium state? A state in which the measurable properties of a system, such as pressure, concentration of the species, etc., do not change with time under a given set of conditions, is said to be a state of equilibrium. Is said to be a state of equilibrium. Again, I repeat, the state in which the measurable properties of a system, what are the measurable properties? Either it is for pressure, concentration, does not change with the time. Does not change with time under a given set of conditions is said to be a state of equilibrium. Right? Yeah. This already you might have studied in thermodynamics, but now here is equilibrium state is same as steady state because the things are not changing with respect to the time. Is it correct? Can I make that statement? Again, it is an open-ended question. Can the equilibrium state be called as steady state? No? Because the things are not changing with respect to the time. Emma? Yeah, that's for you
Well,
to
in
think
case of
and
equilibrium,
answer that question. Yeah, after your answer. What happened? What are the characteristics of a chemical equilibrium? The properties of a system becomes constant at equilibrium and do not change. This is the important thing. The properties of the systems becomes constant at equilibrium and do not change thereafter. The equilibrium can be achieved in either directions. If it is a reversible process, either forward or back, starting with pure reactants or pure products if the time sufficient time is provided. The chemical equilibrium is dynamic in nature. That is nothing but the rate of forward reaction should be equal to rate of backward reaction. Generally, a catalyst speeds up the approach. What is the nature of a catalyst or what is the role of a catalyst? It speeds up the process. That is, it will make the process towards the equilibrium, but does not change or alter the state or position of the equilibrium. That's the big thing for the catalyst. Catalyst speeds up the process, but it won't change the position or the state of the equilibrium. Right? So these are some of the characteristics of chemical equilibrium. You need to know what is equilibrium and the characteristics. It's very important. So, and the equilibrium constants from the thermodynamics, we need to calculate this. This comes in the delta H, delta G. That is nothing but Gibbs free energy. We consider the equation A plus B R. This irreversible process. A Van't Hoff isotherm relates the Gibbs free energy. We know that delta G is minus RT ln K. Ln K is equilibrium constant. If it is a reversible process, then forward reaction by backward reaction you have to write. Delta G is the Gibbs free energy is RT. R is the gas constant, T is the temperature. Where delta G is the standard Gibbs free energy change for the reaction. K is the thermodynamic equilibrium constant. We can write delta G as the sum of the free energies of the product minus the sum of the free energies of the reactants. So delta G is nothing but you can write as delta H minus T into delta S. This zeros is all about standard, right? So don't get confused that. So we can write delta G as delta H, that is the enthalpy, minus T into delta S. Delta S is nothing but the entropy, standard heat or standard entropy change for the reaction. Delta H is the enthalpy. You know these two, then we can calculate delta G, or we can calculate delta G from this particular equation. Right. So what is the time? It's 9:21. So I'll stop here. So this equations, I think whatever I am doing here, I think in thermodynamics you might have got. I'm not going for the derivation and all. We require this equation. Delta G is delta H minus T into delta S. It depends. Your delta G is negative, then we can tell that the reaction is feasible, and delta G is positive. We tell that delta G is not possible. That reaction is not feasible. So for that, we for a gases, we can write activity coefficient. This all I think you might have studied in the thermodynamics. Activity coefficient is F by F0. So for a liquids, solids, here one important thing is delta G. If delta G is negative, that is less than 0, the equilibrium is shifted towards the right, that is towards your forward side, and the yield of the product is large and the equilibrium constant is low, high. If delta is greater than 0, then the equilibrium is shifted towards the left, that is the product side, reactant side, and the yield of the product is very small because the equilibrium constant is very low. This equilibrium constant is low. This, depending on this value of delta G, either you can tell the reaction is feasible or not. That we'll see in the next class, right? I'll stop here. You can see in the next class how that the equation is going to come, how this, what is that equation? Arrhenius equation also going to come. See, this is some standard thermodynamics. It's nowhere related with the reaction engineering. You need to know this, then only we can go for the important thing. This is from here you get our reaction engineering into that we'll start do in the next class. Okay, so I'll stop here. How many people are there? 51 is there, so including me. So 50 people are there. Guru, please take the attendance and submit, right? Okay, I'll stop here. We'll continue in the next class, right? So some basic stuff of thermodynamics is required for the 4th unit. So that's the basic stuff I'm giving you. Then the actual reaction engineering, where with the temperature change, how to incorporate it, I'll discuss in the next class. Okay, I'll stop the recording. Thank you for joining. We'll meet on